before we actually get into answering some questions, the first thing we probably need to do is just check some basic settings for our calculators. The first thing we need to do is make sure that we check the display digits setting on our calculator. I recommend float. The default setting is actually float 6, but that can actually we can run into troubles using that float 6 and getting the answers to the right degree of accuracy with float 6 settings. So I recommend float, and that takes any problems associated away with that. And the next setting I would want you to check is the angle setting for those of you who do the geometry and trig module. Make sure that's set on degree. And probably the last one that you should also check is that your calculation mode is on approximate. All right, and just for a quick reminder on how to do that, I've got my calculator open up here. If we click on the power setting of our calculator and go to document settings, that's where you can make our changes here. You can see I've got mine on float. I'm a bit naughty here. I've got it on angle and radian, so I'll make that change and make that degrees. And then I've got calculation mode. I want that approximate. All right, and I'm going to nothing else I need, so I'm going to press OK, and I'm good to go with that. You should get the setting of make default actually, and I would actually encourage you to make default when you do that on your calculators. But now we are ready to go to answer some questions. So let's kick off with question 1. Now remember, if you didn't download the question sheet, you can do so in your own time and rehash these questions. And also, you're going to have access to this PowerPoint anyway at the later on. Okay, so question 1. The height of a population of Year 12 students are normally distributed with a mean of 170 centimetres and a standard deviation of 5 centimetres. Question 1. A student selected at random from this population has a standardised height of -2.5 centimetres. The student's actual height rounded to the nearest centimetre is, and we've got a whole bunch of alternatives to work through. Okay, now the first thing we need to do is perhaps concentrate on some important information that will lead us to the right direction in answering this question. You'll see here we've got normally distributed, so that we're now talking about the normal distribution. We've got a mean of 170 and standard deviation of 5 centimetres. The next thing we're concentrating here is the standardised height. So that's giving us a hint that we should be talking about z-scores. We're actually being given that value, -2.5 centimetres, and we're actually asked to find the actual height, round to the nearest centimetre. And so how are we going to go about answering that question? And so if I flick to this first page here, some of you may or may not have seen notes pages in action, so I'm going to show you how to do this. But using solve, you can just as easily open up a calculator page and also solve such a question. And so I've actually got the information here entered in. The z-score is -2.5 centimetres. The x value, in other words, the actual height, we do not know, so we have a question mark beside that. The mean is 170 centimetres. I can actually spell the word mean, but the proper word for mean, as far as the calculator is concerned, is a actual calculator function. So I had to put the extra n there so I could actually define it as a variable. And I've got the standard deviation of 5. Now, what happens is it's actually worked out the answer for us to be 157.5 centimetres, which rounds up to 158. And so from the point of view of answering the question that we're dealing with, that would be actually answer D. But before I move on, I'm going to flick back to this page here. How do you use this? Well, if I was doing a different question and the standardised score was instead 2, all I do is click on the maths box like I had, delete the negative 2.5, I press 2, and then press enter, and watch carefully what happens to the screen. You'll see here that the calculation has been automatically worked out. So the actual height now for this particular value is 180 centimetres. But that I could in fact turn around and say, okay, if a student had a height of 185 centimetres or 187 centimetres, that'll do us. I misfired on the keyboard there. And I actually want to know what the standardised score is. All I have to do is put a question mark up there instead and press enter, and I get a standardised score of 3.4. And so this is how a notes page works from a formula base. It's interactive, it's live. You've just got to make the one change, and when you press enter, the calculation keeps getting rehashed. So some of you may be interested in doing that. Again, I remind you, you'll have access to this file for yourselves to have a play with. But in another instance, of course, you could in fact be asked to work out the mean or the standard deviation instead. And so you're just going to put a question mark beside the quantity you don't know and put the information in for the rest. So that probably sums up enough on question 1. So what we'll do now is move on to question 2. Now we've still got question 2 is still related to the same information. The heights of a population of Year 12 students are normally distributed with a mean of 170 and standard deviation of 5 again. Another student is randomly selected from this population and has a standardised height of 1 centimetre. The percentage of students who are shorter than this student would be closest to. Okay, so we're still talking about the normal distribution, but now we're looking at, if we look at some of the key words here, the percentage that is shorter. All right, so there are a couple of ways we could perhaps look at doing this. So if I now flick back to my calculator, I'm now going to go onto the second page here, or the second problem. So this is problem 2, and it's made of 1 page. What I've done here is this page is actually our 68, 95 and 99.7% rules for the standard deviation. And I've entered in the mean and the standard deviation here. As you can see, 68% lie between 165 centimetres and 175 centimetres. Which begs the question, if you go back to the information, it says has a standardised height of 1 centimetre. Right, so therefore, that 1 centimetre is suggesting that that's 1 standard deviation to the right of the mean. And so that would sort of tell us that, in fact, that corresponds to a height of 175 centimetres. And so what we've got here is 68% lie between 165 centimetres and 175 centimetres. Does that actually answer the question? If I go back to the problem, it says here the percentage of students that are shorter than this. So we want the percentage of students who are shorter than 175 centimetres. And so what we probably need to do is go back to our page and keep reading. 95% lie between 160 and 180 centimetres. That still doesn't do it. So I'm going to scroll down a little bit further. This is an interesting line here. So 16% lie below 165 centimetres and above 175 centimetres. Well, that is interesting. 16% lie above 175 centimetres. If that's the case, if I subtract 16% away from 100%, that would tell me that 84% lie below 175 centimetres. And so if that's the case, that would suggest that the answer is B, 84%. All right. Now, if I go back to that page, if we're doing a slightly different question, I could, in fact, change this to 180 centimetres. So I'll make the change and press enter. You can see that the information automatically gets updated here. So if I change that standard deviation to 2.5, the information automatically gets updated. So it's a nice, simple resource to use, and we can answer such questions. What I'm going to do is change that back to 170 centimetres. I do need this information. Next, so station of 5. Don't forget, if I'm going a little bit too quick, you'll be able to replay. You get the copy of the webinar and replay it at your own leisure. Now, if I go back to my slideshow, so question 3, the heights of a population, same population. This time we've got a sample of 300 students were selected from this population. The number of students to measure between the heights of 165 centimetres and 180 centimetres is closest to. Okay, so what are the key words here? We've got normally distributed again, standard deviation, mean. So it's still, we've got the key triggers that it's still the normal distribution question. This time we've got a sample of 300 students, and we're going to find the number of students between these two heights. Okay, so how can we use that resource that I've just shown you to do this? So what we need to do is, again, have a look for these figures. 68% lie between 165 and 175. It sort of looks okay, but the only trouble is 165 is what we want, but 175 is not what we want. If we have a close look, the 180, which is what we want, is actually on the next line. So what I'm suggesting we need to do is actually go down a little bit further and use this information here where my screen is hovering over. 16% of the data, or 16% of the population, lie below 165 centimetres. That's what we can get there. Now we can also get from the next line down that 2.5% lie above 180. So in a simple sort of analyse what we did before, if that's the case, to get the percentage in between that figure and that figure, we're going to go 100%, take away 16, take away 2.5, right? And once we get that, it's a matter of doing the calculation. And so basically, if you go, what I've done down the bottom here is gone 100, I've converted a percentage into decimals. And so if I do that, I'm going to delete the 300 for a second. If I go 100% take away 0.16, take away 0.025, which is 2.5%, you get 0.815, or if you like, 81.5% lie between those two numbers. And then what I'm going to do is then get the calculation and then multiply that by 815 times that by your 300 students, and you'll get 244.5 students, which rounds up to 245. Again, I'm using a maths box here to do the calculations, but you could just as easily do that on a calculator page. That's not a big deal. But probably learning how possibly you might find that using this page could be quite useful. But that aside, if we go back to our PowerPoint, that corresponds to answer A. Okay. Next question. So the following information refers to questions 4 to 6. The scatter plot below displays the result for a group of Year 12 further maths students and the time spent studying for their SAC. So let's have a look here. It's been cut off the screen there, but we've got SAC score here on the vertical axis. So that's our response variable. This is study time along here, along the horizontal axis, which is the explanatory variable. All right, so let's have a look here. The residual corresponding to the student who spent 3 hours studying for the SAC is closest to. Okay, so let's have a look at some key words here. Scatter plot. So we can identify the fact that a scatter plot is in fact related to some bivariate data where both variables are numerical. Now, when you start looking about a scatter plot, you've got to look at other things too, like the sort of correlation that we've got. This is a positive correlation, but of course you've got negative correlation. Some of the other key aspects that we actually have to look at is the form, whether it's linear or non-linear, and the strength of it as well. So this is a fairly strong sort of correlation, but you've got weak or moderate as well. So they're the other things that when you see the word scatter plot that you need to have in the back of your mind some sort of understanding of those key terms. What we're also looking for the residual, I've made a little bit of a mistake here, probably should have had the residual. There's a key word here, residual, corresponding to a student who studied 3 hours. So 3 hours, if I come down to the screen here, 3 hours is here. If you look at my pointer, if I scroll up to here, okay, so we're talking about the distance. The residual is the distance between the line and the actual data value. This is the actual data value here, all right? So this is the residual from here to here. Now, you've sort of seen in the textbook, to calculate the value of the residual, it's the actual number, which is 15, take away the predicted value. The predicted value is the value that lies on the line. Now, that's, as you can see, that's roughly, it's approximately 12. So if we go 15, take away 12, then the answer is 3. And so that would seem to correspond to answer D. Okay, now if we move on to question 5, again, same scatter plot. This time it's looking for the equation of the least squares regression line. Now, in some instances, when you get a question like this, particularly from a multiple choice aspect, sometimes you don't need the calculator to answer it if we sort of have some basic understanding of the information that's being given us. For a start, I can see that this is a positive correlation, so the gradient is positive. All right, and so if we look at it, anything that's got anything in here that's got a negative gradient, we would automatically discount. So if you have a look here, I've got negative gradient there for alternative B, and I've got negative gradient here for alternative E. So I'd be ignoring those. The other thing to look for it too is to say, well, the SAC score here is the response variable and study time is the explanatory variable. So if that's the case, we'd only be looking for, if you like, alternatives here that's actually got SAC score as the response variable. So with all that in place, we're now sort of down to making a decision between A and C. Because don't forget, we've got rid of B because it's got a negative gradient. Right? So if we now have a look at the scale here, we can see that, in fact, this value here, starting off at 0, if you have a close look at the scale, that's x equals 0. That's therefore telling me that this is actually the vertical intercept being 8. So here we are. It's got to be alternative A as the answer. So without actually getting our calculator out, we could, in fact, arrive at such an answer, some basic maths understanding. Be really, really careful here, though, about this here. Not all questions, and you've possibly seen some during the year, necessarily start off with the explanatory variable being at 0. Be really careful at that, right? Because if that's the case, and that's not, then that point there is not the vertical intercept. So keep a real careful eye out on that. Having said that, that whole explanation that I've just said, some people may not necessarily understand it. So how else could you go about answering the question? Although it'll take a little bit of time, what you could do, because you've got the scale here, you could put those numbers into a list and spreadsheets page, because you've got the scale there, and do the least squares regression line on it. That's an option. However, I reckon there's actually a quicker option to do that, and that's what I intend to show you. So if I go to this next page on my calculator, it's this one here. Again, it's a notes page. This notes page here is asking you to, in fact, put in 2 points. Here's the first point. You've often seen points described as x1, y1 and x2, y2 in the past. Now, what I've done is I've identified 2 points, the point 0.8 and 4.13. The question you might be asking is, well, where am I getting those 2 points? So what I'll do is I'll flick back to the screen. So the first point being 0.8, well, that's the intercept, 0.8. There it is there. All right? So that would be the first point I would use. It pretty much fits the scale. All right? The other point I used was point 4.13. So I come across 4 and go up to 13. There it is. You can see the line is going pretty close through the corner of that square. So that's pretty close to the point 4.13. So I'm taking a punt that that's going to go, if I use those 2 points, that's going to actually go close to giving me the equation of the line of best fit. And so now if I go back to over here, I've put the 2 points in, and if you have a look here, it's given me the equation here. The response variable equals 8 plus 1.25 times by EV. Now, it's not quite the same. It would round off to 1.3. But don't forget that at least one of those points wasn't exactly right, but it's close enough to actually give us the right answer. Now, if you're wondering about how this works, because I actually haven't done anything on this page, I'll show you. So I'm just going to change one of these numbers, a couple of these numbers. If I change that to the point, make that 0.18, watch what happens when I do this. If you watch the screen closely, everything gets updated. Just making that one change is now updated that. So this page is all about asking you to put in the coordinates of these 2 points. So if I change that and make another change here, I'll make that 10. You can see it automatically gets updated. What I've also got here, for those who would be careful, is given the value of R. So if I punch in the value of 0.6 for R, then the R squared value gets calculated for you. I think that's not a huge drama about doing something like that. You could easily do that on a calculator page. Given R squared value, so if I give the R squared value of 0.8, then you get an R value of 0.89. But be really careful about these ones here, given R squared, because don't forget, given R squared, the R value could be a positive value if it's a positive correlation, or it could be negative if it's a negative correlation. Don't forget that also corresponds to a positive gradient in the equation, and being a positive R value, and a negative R value would correspond to a negative gradient in the equation. So there's just little things you just got to watch out for when doing something like this. Okay, so when it's all said and done, if we go through this, again on the PowerPoint here, I've sort of jumped ahead a little bit, but the key word here is, of course, the equation. I've shown you how to find it, and it ends up being alternative A. So we'll move on. Next question, the scatterplot below displays the results for a group of students again. This time the coefficient of determination is 0.76. The correlation coefficient R is closest to. So given the coefficient of determination, which again, if the key words that we are trying to look for, given the I'll start again, the coefficient of determination, we're trying to find the correlation coefficient. So 0.276 is the coefficient of determination. So we go back here. So coefficient of determination, 0.7726. That gives me my value of R. But whoa, must be careful. Like I said with this, I've got an answer 0.85. I think I better go. We need to go back and check the scatter plot. And so we probably don't really need to. We've already seen it. It's a positive correlation. So therefore, the value of R is going to be positive. And so the answer in that instance will be B. All right. So moving on to the next question. Question 7. Following information is used for questions 7 and 8. A set of experimental data is recorded in the following table. There it is. To linearise the data, a reciprocal transformation to the y variables performed. The least squares regression line is then fitted to the transformed data. Equation of squares regression is closest to. And we've got a whole bunch of alternatives there. So, if we look at this from the point of view of some key words, linearise the data, so that's giving a hint we've got to use the least squares regression line. But they're saying we want a reciprocal transformation of the y variable. In other words, that's 1 on y. So, in other words, the y numbers up here in the table have to be reciprocated. In other words, it's 1 divided by 106, 1 divided by 49. Etc. And they're also telling us that x is the explanatory variable. Now, because of what we've just said, that basically you're doing a reciprocal transformation of the y-axis, straight away there are 3 alternatives we can actually get rid of. B, C, and D. We're now making a choice between A and E. So what are we going to do from there? Well, what I've got is a file that, I need to move that over there for a second. A file that could possibly help us with this. Now, what I've done is, to save a bit of time, is I've actually automatically punched these numbers in. So the table here, XEV stands for the explanatory variable, which happens to be on the x-axis. YRV stands for the response variable, which is on the y-axis. Now, if I go across to the next page, we've got the scatter plot. So that, as you can see, there's clearly a curve. That's clearly curved data. It's certainly not linear. That's non-linear. So what we're supposed to do is actually perform a reciprocal transformation. If I click on the y-axis, the YRV here, the response variable axis, and choose 1 on y, because we're supposed to be doing that transformation, we now get that data transformed. Okay, and then if we have a look up here, there's the equation of the transform or the non-linear equation, but you've got to be really careful in reading that. That's 1 on y, because that's the transformation that we've actually occurred, equals all this here. What some people like or don't like that, the next thing over here is I've actually got the exact same data being calculation here. Here's your A value, here's your B value. So in other words, it's 1 on y equals negative 0.09 plus 0.013x. That would seem to suggest, if that's the case, if we go back to here, it's alternative E. Now that's all well and good, but you actually I haven't shown you how to use that page. So bear with me for a second. I'm going to go back to the very first page, 4.1 of this. What I'm going to do is clear the data. All right, so I'm going to highlight that there, highlight the formula bar, press Control Menu, and I'm going to clear the data. And then I'm going to go Control Menu and clear the data again. There it is. All right. So now what I'm going to do is I'm just going to put a few numbers in to demonstrate what I'm doing. So I'm going to put in some numbers 1, 2, 3, 4, 5 will do. And then I'm going to put in 1, 3.9. Whoops, no, I'm going to make that 3.9. 8.7, 15.5, and 24. Now, once I've actually completed all that, there are some things going on here. The residuals automatically get calculated to what's actually going over here. I'll come back to that. More importantly, we need to actually scroll across. Automatically being calculated is the x squared transformations. In other words, all those x numbers in XEV have been squared. You can see the formula being used there. If I scroll across, the y squared, the y numbers are being squared, or if you like, the response variable numbers are being squared. Then you've got the log x transformation, the log y, 1 on x, and 1 on y. It's actually all there and stays there. That's the whole point of, I guess, creating files in advance that we can use. All right. Now that I've done that, what I'll do is first of all just display the original data. So if I go to YRV, there we are. That is the original data, right? YRV being the response, XEV being the explanatory variable. As you can see, it's actually a little bit non-linear, that one. All right. And as you can see, the line of best fit is being placed. So at the moment, that's the line of best fit. That's the R squared value. If I go to this page over here, what I'm going to do is on the x-axis, yes, I've got all this data over here is XEV, but I want to actually have on the y-axis, on the explanatory variable, YRV. So on the y-axis, I need to change that variable. So I've just clicked on that, delete it, hit the var button, and just scroll down and find YRV. There it is there. Then press enter. Whenever you make changes in math boxes, you've got to press enter. And I've actually hidden those so it doesn't clutter the screen too much. But if you have a look at these numbers here, they are exactly the same as those figures here. All right. There's your R squared. There's your R squared value, and there's your R squared value there. If we go next, I've got the residual plot here. So when you do the residual plot, you'd always, and this is the same for any of the data and stats page when you do the statistical information, you always get in the habit of when you make changes, go to zoom and then zoom data. So it actually rescales to make sure it fits all the data. You can clearly see there's a pattern in that residual plot. So then how do you make the changes? Well, I've made a decision that I don't think, in fact, this here is the most appropriate linear representation of this. So it's obviously non-linear representation. So I'm going to try an x squared transformation. If I scroll down there, there's my x squared variable there. I'm just going to make that change and see what happens. Oh, look at that. Nice. Looks pretty straight to me. And there's the equation automatically worked out for us. But be really, really careful. Remember, this is now y equals 0.06 or 7 plus 0.96 times by, if I move that time, it won't, oh, it's gone, times by x squared. Which is why we've got to be, again, if we go over here, I've got the information, I'll recalculate it over here. I'm going to make the x-axis the x squared variable. Whoops, wrong button. I'll hit escape. var. Escape is a good option when you make mistakes. And for that matter, undo as well. And so what am I doing? I've lost track of my thought process there. I think I'm doing x squared. There we are. So on the x-axis, I'm plotting the x squared numbers. I've made the change. Don't forget to press enter. And when I pressed enter, you would have noticed that this information down here has changed. So now it's y equals a plus b. It's x squared. Remember, we're swapping the x for the transformation, x squared. All right, and then scatter plot. If we have a look at the scatter plot, sorry, the residual plot, I should say, zoom data again, we get a more appropriate residual plot. I hope that's actually demonstrated how to use that page. I actually think that's a bit of a biggie to learn how to use because it's there for you. You just got to change the numbers and go with it. So it's a good one. All right, better actually keep moving. We're over halfway through the night and I'm not halfway through the questions. All right. So the answer is E. Okay, question 8. Using this equation, the predicted value of y when x equals 5 is closest to. So we're using this equation now. So if I look at the key information here, and we're using this equation, the predicted value of y. So we've got to find the predicted value of y when x equals x equals 5. So how do we do that? I'm going to go back to this calculator, and I'm going to go to the next page. And I reckon this is a bit of a big one too. It looks more complicated than what it is. The first thing I need to do is for that transformed equation, which was alternative E, right? It was the equation 1 on y equals A, which is negative 0.009, plus B, which is 0.013, times by x. So that's the A value and the B value you just entered in. The question is asking us, predict the value of y when the explanatory variable is 5. I've just punched it in. So what do we do? Well, once you punch that information in there, and I put a question mark beside RV because I don't know it, all I do is scroll down. Just scroll down. Have a look at this. 1 on y. So the answer is 17.9. Right? Or if you look at the answer, that would be 17.9. That would round off to 18, which is A. All right. So if I go back to here, how's this used? Because again, you haven't seen me make any changes. For a start, I plugged my A value and the B value there. What if I actually make a different prediction? What would be the value of y if x equaled 7? So I just put 7 in for the EV. Scroll down to 1 on y. There's the answer. Or alternatively, what if we get a nasty question where we know what the RV value, it could be 15, and you're asked to work out what the value of the EV is. So put a question mark there instead. And there it is. There's the answer. All right. You've also got all the other. It's just a matter of putting in the information in and reading. And you'll see you've got the linear model there, as well as all the possible transformations. All right. So I'll keep moving. The least squares formula is next on the page, so that must be a question coming up. So I'm going to go Control and tab it there. Right. Question 9. The statistical analysis of a set of bivariate data involving the variables x and y is displayed in the following table. Use this information. The value of the correlation coefficient R for the set of data is closest to. There have been some exam questions in the past similar to this. All right. And so what we need to be able to do is work this out. So if I go to the next one, next slide, it's not working for me. There we are. So again, it's bivariate data, and we're looking for the correlation coefficient. Now, you could use solve on the calculator page to do this, or if I come over here, oops, I've given the answer away, C. If I come over to here, it's a matter of chucking in the information into this page and then reading the answer out when it's all said and done. And so the mean, which is called X bar, is 28.1. Where do I get that from? Well, if we go back to the table, there it is there. The mean of X is 28.1. Mean of Y is 33. So if I talk about there, the mean of Y is 33. So I've filled in the rest of the information. You're actually after the correlation coefficient. So I'm going to put a question mark there. So all you've got to do is then decide, well, which of these formulas do I use? Do I use this one here? So I'm taking care of looking at that question mark there or that question mark there. Well, I would pose the question to you, which of these two formulas has got R in it, which is what you're trying to find, and the other information that we know. We know B, where B, remember, is the slope. So where did I get that from? I don't know if you can see that because I think that's being hid. The slope is 1.52, which is on the equation. There it is there, 1.52. So that's where I've got that information from. That's the slope. And so if I go back to this, the slope is B, we know that. Standard deviation of Y and X, trying to find R. So there, 9. Again, if you want, making some, I'll show you how to make the changes on this page here. Let's actually pretend we don't know what the slope is. So I'm going to put a question mark beside the slope because I don't know it. And I know that the R value is 0.8. So if I now go down, there you go, the slope is 1.22 and the vertical intercept is 1.13. All right, and so back to our presentation. When it's all said and done, the answer was C, which was 0.996. Righto. Question 1011. We've got a table here of ice creams sales. Use the for mean smoothing with centered to find the number of ice creams sold in week 5. Closest to which of those alternatives? Okay, so for mean smoothing is the key words here. Centering and smoothed. So how can we do this? I've got a nice little resource you might want to try using. So it's over here. The idea is you put in the time values. So where do I get, so I've got time values 1, 2, 3, 4, 5, 6, 7, 8, 9. Why is it the case? Because if I click back here, you've got weeks 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I'm putting in the numbers of ice creams. So sales, there are those numbers there. They're in a list, and you just separate each number by comma. Now, if we go back to the question says, what's the smooth value for week 5? All right, so week 5, there it is there. So all I do is put in the T value, week 5. Take notice that all these calculations are automatically done. And if I go down to the 4-point moving mean, there it is, 329, which corresponds to alternative C. Right, so if I go, I'll keep on moving because we're sort of running short of time. Question 11, the table below shows the number of ice cream sold in a shop over a 9-week period again. This time the 3 means smooth value for week 3. So if I go back to that same page, this time it's week 3, so the time value is 3. Press enter. And you can see you've got all these alternatives here, but there's the 3-point, what are we after? I've lost it, 3-point moving mean. There it is. It's, what am I after? Week 3. Oh, week 3. Week 3, 3.240. I think I must have made a mistake here somewhere. Up 200. Oh, there it is. 220. Oh, I'm looking at the wrong one. 3-point moving mean 227, which is alternative A in our on our presentation. Alternative B. Sorry, alternative B. Righto. Question 12. The quarterly sales figures for a business in millions of dollars, 2017-18 are shown. There they are. Use these sales figures to calculate the seasonal index for quarter 2. So if we're going to do that, I've got a tool here that allows us to do that for 2 cycles of data. Here it is. All we do is for the first cycle of data, which is the first year in this case, you punch in the numbers. All right. So that year 1, that Y1 is basically the first year. Y2 is the second year. Down here, this is like the seasonal indices worked out for the first year. Now remember how to do that. You've got to divide each of those numbers by the yearly average. Gives you those. And the same thing over here for year 2. Year 2, get those numbers, divide by the yearly average. And then the actual seasonal indices, remember, is the average of the corresponding seasonal indices. So the average of 0.76 and 0.66 is 0.71, which is your seasonal index. So again, it's basically, this is automatically works something out for two years. It's a matter of deleting the data and punching it in. So if I change that to 0.8 and press enter, we get some changes. What you could do if you wanted to is actually do them one at a time. So I've got just one cycle at a time. So there's the first year punched in. What you could do then, so that's, if you like, that's the seasonal indices for the first year. Then if I delete all those and punch in the figures for the second year, 1.04, comma, 2.46, comma, 2.06, comma, and I'm missing one, 0.78, 0.78. There's the season indices for the second year. And again, all you got to do then is, all you have to do is average the two of them together, the 2 separate results. So it's a bit more work, but it's a bit more flexible, this, just in case you've got 3 or 4 years worth of data. In the end, when you work through it all, you get an answer of C. Okay, so we'll move on to question 13 and 14. So on to a little bit of recursion stuff. The value of an annuity investment where interest is paid monthly and payments are also made monthly can be modelled by this recurrent relationship. There it is. The value of the annuity after 3 months is, okay, some key words. Oops, wrong button. Key words, it's an annuity investment. So therefore notice the plus 500 there. That's a key thing that we need to know. We're making monthly payments. So everything is going up from a monthly point of view. And it's a recurrent relation. So that's your standard form for a recurrent relationship. You've got the starting off value and you've got how it's changing over time. Right, so remember that, so the starting off value is how much has been initially invested. All right, so how can we actually go about answering this question? Sorry if I'm speaking a bit too quick, but time is marching on. Right, so if I go on to here, recurrent relationship. Okay, $56,000 I've plugged in there. All you do is just make changes, press enter like before. There's the R value, there's the D value, there's the recurrent relationship. So that's exactly what was in the question. So the question says, what's the value of the annuity after 3 months? If I go to this next page, I scroll down to 3, there's the answer. What I've got here generated is the first, 9 terms. In fact, I'm going to fill down. If I press Control, Menu, and Fill, then use my down arrow key and press Enter, I complete the pattern. And so, if I go back up to there though, after 3 months, there it is, there's the answer. All right. Alternatively, if we go down a bit alternatively, oh no, there is no alternative. I've lost the plot. Okay, that's the way to probably answer that sort of question. You could actually just do a step-by-step calculation on a calculator page. It achieves the same thing. All right. Next, the next question. So the answer is E. Next question. The value of the annuity investment is also over that. The increase in the value of the annuity between the third and fourth year. That's really important. Focus on the increase in the value of the annuity between the third and fourth year. What does that mean? So if I go back to here, this is the value of the annuity in the third year, after the third year. This is the value of the annuity after the fourth year. And so if you work the difference out between those, so just go that value, take away that value, you get $750. That happens to be that number there. I've just used the formula. Don't bother doing that. All you have to do is understand the fact it's just the difference between those two numbers. So you can actually just work that out by hand, right? That's quite useful being able to at least see that from the point of view on the spreadsheet. Next question. I know I'm rushing a bit, but we're getting there. Don't forget, you can download this webinar and play it at your own leisure, a bit slower. Use the following information to answer questions 15 and should be 15 to 17. Sorry about that. Car is purchased for $35,000. Over time, its value depreciates using the reducer balance method. The car depreciates at a rate of 7.1% per year. The recurrence relationship that models this would be, righto. So, keywords, $35,000, depreciates, reducing balance, 7.1%, and we're looking for the recurrent relationship. You see, all this is forms of recurrent relationship. So, what do? Next page. This is an example. Recurrent relationships is where you're actually doing recursion where you're multiplying by R, and I've got different sorts of problems there. So, if you look at the question, $35,000. So wherever it says V0, you'd be making alterations to $35,000. So there it is, $35,000. We're told what the rate is. So here what you would do is you put in 7.1 and press enter. Now for reducing balance depreciation, the compounding periods per year is treated as 1. So you would treat that as 1. Now, there are two values of R being calculated here. R for, if you like, interest or increasing. In other words, where the values are multiplying by a value bigger than 1. Or if you like, the decay scenario, which is what the depreciation is. There's our R value there, 0.929. So if I put 0.929 there, I'm not going to delete it all. I'll just put that in there, press enter. Have a look what happens here. The recurrence relationship actually gets displayed. So that actually corresponds to alternative B in our alternative, alternative alternative A it is. It is alternative A. I misread that. Alternative A on our screens. Righto, I'm running out of time, so I'll try and finish this off as quick as I can. A car is purchased for $35,000. Over time, it depreciates. It's the same information. What's the value of the car? The value of the car after 5 years is closest to. All right. So you want the value of the car after 5 years. So what I'm going to do is back to here. So if I go back to this table again, there's the value of the car after 5 years. All right, $24,218. And so if we go back to our slide show, that would be answer. That would be answer. Hopefully, we did it. Now the question 17. A car is purchased for $35,000. Over time, same information. The depreciation during the fifth year is closest to, here we are. So during the fifth year, so if I go back to here, during the fifth year would be the difference between this value and this value, the value after 4 years and the value after 5 years. So if you, again, like before, work out the difference between those, you get actually 8,000. So again, $1,850. And so I wouldn't worry about that. Just do the calculation by hand and work out the difference. And in that instance, you'll end up with alternative E. Now, I do believe we've run out a little bit of time and haven't quite got through the questions. So 18, 19, 20 to go. So I'll leave you to have a go at those. Sorry I didn't quite reach there, but we had a little bit to cover. I certainly hope that you got something out of tonight.